पासपोर्ट घेता है वो मैं 2 लोग था बोलून घेतो अगर म्हणून पिताच्या तुम्ही तुमच्या ह्याच्यात ठेवायचा बायोडाटा हे बघा म्हणा दाखवत जे उंची उंची आहे फोटो ती इच्छा असेल ना आपण काय आपल्या भाषेत बोलायचं आपण ते आपण आज जुन्या आदिवासी त्या म्हणा त्याला या त्याला म्हणा आदिवासी आपल्याला आपण जास्त का नाही केलं
What was the class earlier to this? Yes, everybody can respond. Am I audible to you all? Am I audible to you or not?
Yes, sir.
Okay, what was the earlier class? Earlier to this? Okay. So was it, I think it was left on time, right? How much time before the class was ended? Before 10 o'clock? 5 minutes earlier? Okay. Then why it is so that at 10:05 only 108 students are able to join? It's already 10 past 5 now. And only 109 students have joined. I'm not going to let the other students to get into the class now. Okay, let us start the discussion. So what we have started for in the last lecture is the errors into the measurement system. See, what we have started discussing is the measurement system that are used for measurement of some entity might have certain own inaccuracies into the measurement process. and those we must be able to know. We must know it. Unless we know and classify, we will not be able to eliminate the malfunctioning of the system itself, the measurement system. There are many components, the functional components as well as the physical components available, and then they are going to perform inaccurately if there are some errors into the measurement. So what you have seen in the yesterday's class is the error is nothing but there is some deviation from the desired conditions. So the error is nothing but the difference between the measured value and the true value that we can notice into the end result. But again, for knowing the true value and the difference if there is between the true value and the measured, it becomes very difficult to know. Say for example, now there is a distance measurement using the micrometer. We are trying to know the length of the particular bar, particular component. We are trying to know the temperature of the system. We are not knowing what is the true value of the entity status at that particular time of measurement. Right. So when these entities are not known, the true input is not known, we cannot believe closely on the output shown by the measurement system. If the measurement system is showing that the temperature is 25.2 degrees Celsius, so it is actually closeness between the true value and the output shown or displayed by the instrument. So for that reason, we must try to analyze the different causes that can easily be allocated on the instrument point of view from the measurement system point of view, and that can be as far as possible try to correct it. So many times what we do is we give repeated same input to the measurement device or measurement system, and then we try to find how the response of the system is there, how it is going to give the output, and we note down the output at each and every time, and then we use some tools, some techniques for knowing the difference that has been caused. So then that difference may be because of a little change into the system entities. Say for example, temperature might be fluctuating over say 5 seconds or over the 10-second time by means of some value. So that is also going to reflect on the output. So starting from that, there can be many mistakes or many say peculiar functions of the measurement system itself, which is going to cause the error into the system. So we first of all try to find out or try to say quantify, try to understand what are the different kinds of errors that can be present into the measurement system itself. Right. So what is the definition we studied in the last class is a gross way of defining the error is the difference between the true input, the true value, which is always in question because we do not know the true value at any instance of time. But whatever is the true as far as the understanding goes, as far as the say quantification is concerned, whatever shown for the given standard, now in this case we use the standard value. If suppose some standard value of the entity is applied as input, we can understand the response given by the measurement system. So in this condition, whatever value shown on the display panel to the standard set input, that can definitely be used for knowing the type of the error that can be generated. We can quantify that. So the types of the error, say basically we are going to find out the possibilities of the error from say measurement system point of view or measurement system point of view, we can call the instrument point of view. Right. So there are certain entities which are going to act simultaneously and is going to have some kind of sign over it. Say this kind of error sources can be called as a systematic or a cumulative kind of error, as we discussed in the last lecture. So systematic is nothing but it is possible to classify in a very methodological way. We can know that if there are certain say procedural steps present during measurement, we can assure that there can be some kind of error, or otherwise some kind of error can be avoided from entering into the system. So such error have some kind of magnitude, either plus or minus sign, and some magnitude, some value, some mathematical value can be given. We can find out that in terms of some quantity, say 0.1 millimeter of the error into the scale, or 0.05 millimeter error into the vernier caliper, or say 0.5 degrees Celsius measurement error into the, say, temperature measurement devices or temperature measurement system, and so on. But they behave more or less systematically. So the peculiarity of this is it is going to add. Say if there are 5 or 6 different sources of error, as we discussed in the yesterday's class. Suppose it is a systematic error sources, and the error sources are, say, 1, 2, 3, 4, and so on. Each one will have its effect on the measurand, the quantity that is displayed, and that can be quantified. Say example 0.1 is the error, systematic error induced because of the system or the source 1. Because of source 2, suppose now another 0.05 units of the error is incorporated, then it will have sign, either it will be plus, minus, plus, plus, and so on. And at the end, it is going to have a total effect. So summation, algebraic sum of this is taken, so that is going to show some output value, say for example 10.025 something. So this is how is the total or the end result of all types of errors for the systematic or cumulative errors. So the peculiarity that we have seen in the yesterday discussion is the error tend to add or subtract depending on the sign that is being used there. Right? Such errors alter the reading by a very fixed magnitude. Say once, for example, we have applied some known value that we call as a standard value, or a measured value is given as the input to the system, then we can find out the behavior, the output shown for each source. Now if we change the value, say if you identified that this is some value shown, say for example 0.1 is a total error shown as a systematic error for input of 10 inputs or 10 unit input to the system. Then if it is 20, probably it will become 0.2. This is how we can, it is shown from the mathematical analysis that this is a very, say, known or very predictive behavior of this kind of systematic and cumulative error. So what we identify that there is very fixed value change with respect to change in the input. If I apply 15, then probably it can understand that it is going to become 0.15 as the error shown on the instrument. So we can have a very close relationship between the input and the error that is being governed, that is given. So it is very fixed magnitude. And the sign also is very predictive. It can be either plus or minus only at the end as a, say, total sum of all the sources of error for systematic or cumulative error. So many times it is called as a bias. I think that we'll come to know under the static characteristics of the instrument. What is the meaning of bias? So we can very predict the instrument characteristics for the small input and subsequently change the input, how the output is going to change, that can be identified. Okay, so that is called as a bias. So this very first kind of error, that is, first of all, we must know the names itself and behavior patterns, a systematic or cumulative error. Then there is one more that is called the random. Let me know any doubt in understanding. I have repeated that because it was, say, covered in last few minutes of the last class. So if there is any doubt, you please let me know regarding the systematic or cumulative error. We are going to discuss that again in detail. Right. So let us try to move ahead. We'll go to the next type of error, that is the random error. The name itself suggests that it is a undecided pattern, undecided magnitude as well as sign of the error that is displayed at the output of the instrument. So name itself says it is random. It is going to occur randomly. So there is no consistency. As we can have a very correlation between the systematic and the cumulative error, that is going to vary, very broadly vary with respect to the input. Larger the input, proportionally larger will be the effect of that on the end result. Whereas there is no consistency in the error if it is a random error, we call. It is going to occur accidentally. So errors vary in the magnitude. Many times the magnitude vary, the magnitude quantity varies, as well as the direction also varies. Sometimes it is going to add the error, sometimes it is going to reduce the error. So if there are many sources for random errors, then they are going to behave in very different patterns. So we cannot quantify that. We cannot say quantify that for different sets of calibrations. Right? The error varies in the magnitude and the direction for given set of conditions. If the condition set is changed, we may find it is going to have different effects. Say for example, operating temperature and pressure condition, the pressure that is applied on the instrument, if the person is going to change, again it will have some different reading. Say many times we do not have agreement. Suppose some reading is taken from the measurement system by one particular person. To get the confirmation, if it is asked to be say measured by other person, probably it will have some deviation. Right? So there are different reasons for it. So in actual practice, the behavior is again in the form of algebraic sum. Say error because of source 1 plus minus error because of source 2 and so on is taken into account and is going to govern the final error. So at some point of time, in some condition, it is going to have different value of E, different sign of E. Right. So actually in the end, it is going to say have the compensation. So totally it is going to have some kind of adjustment. Some error sources may magnify error, some error sources may reduce, and the total contribution will be the algebraic sum of that. So it is going to compensate. So also known as the compensating error. So due to the random variations into parameter or system measurement or condition in which measurement is taken or the environment where the instrument is operated and so on, possibly this kind of accidental errors occur. We are trying to know, say as a measurement science or the measurement technology person, we try to identify what can be reason, and it is going to vary with say wide variation. For the different measurement system, there can be different causes of random errors. Right? Then there can be error above and all the sources which are very unpredictable, which can neither be called as random, which will not be called as accidental. Say for example, what is common in between the random and the cumulative sources of error? That they have some sign, they have some magnitude. In cumulative error, they will have same sign and magnitude goes on varying, and then in the end it is going to be the cumulative sum. In the random, we do not know even sign, either it can be plus or minus, and magnitude also going to change. So it is going to compensate. But in case of the miscellaneous error, it is totally going to behave in some different fashion. It may be proportional, it may not be proportional to the given input. Right, here in this case also there is no proportionality. Suppose I am going to change the standard input with a regular interval, say 0.1, next 0.2, 0.3 and so on, say till 0.1. There are 10 fixed value of the input that are given to the system. For random error, we do not know that whether the error because of that source will be proportional to given input or not. Say for 0.1 it can be something higher, or 0.2 it can be something lower. Again 0.3 it will be something else. So in the miscellaneous, even that is not known. So there is no method, there is no way that we can identify the source of error, but at least we can have some discussion or some probable situations which are going to cause the miscellaneous error into the system. Right. So let me know any doubt in understanding the only broad way or classification of the types of the errors, the cumulative error or say uh, systematic error, random or accidental errors, and the miscellaneous error. Let us try to understand these in detail, right? So coming to this systematic error, what can be reason for this? We identify, we have found on having multiple readings possible on the measurement system, we have found that the error can be basically into the measurement system. For example, there is some measurement system of temperature, say for example thermometer, then we call that as instrument, thermometer as instrument, then there can be instrumental error, right? Then there can be some factors which are because the environmental issues, like change the pressure, temperature, or say other kind of, see it is an optical instrument, suppose now there can be some kind of dust, smoke and other element present, say there can be some waviness into the glasses and so on, so that the graduations will not be seen clearly, there will be some ambiguity whether it conforms to the upper line or the lower line and so on. So there can be some different environmental effects, and there can be loading error. Now loading error, I think we have discussed something in earlier classes, right? So the meaning is, if we take proper precaution, proper procedure is adopted, and that is why we find into the measurement practicals there is some way of having the standard set procedure for carrying out the measurements. The measurement process is such that we try to minimize this kind of unwanted sources of error to contribute into the output reading. So this can be eliminated or corrected, or at least they can be quantified. So that's what we have seen. So once it is quantified, we can think, say for each measurement, suppose my input is 10 and it is showing 10.01. If my input is 20, it is showing 20.2. Then we know that this 0.1, 0.2 in the second decimal is nothing but the error. So we can directly subtract that. So that is what is correction. The output that is known, if we know the response given by the instrument is going to be differing by a fixed quantity for a given input, subtract that or add that, and we can have corrections over the say instrument. So the random errors are inconsistent and it is associated with the measurement, accuracy of the measurement of small quantities. If the input is going to vary with a small value, how faithfully the small quantities are going to reflect. So there are many characteristics of the instrument with which they are able to sense something, a large input given, and after that large step of input given, if small value is given, it may not be probably responded in the output value. So it is an inconsistency that is related with the measurement of small quantities, and that is why the input is planned. The scale of the instrument or the measurement device display panel is designed such that it is going to take a proper care of a small entity that is given as an input, which should be reflected as the output. Right. So into the random errors, the instrument or measurement system is framed such that the small input that is given shall be faithfully represented and it should not be lapsed out. So this we are trying to reduce down the inconsistency. We are going to make the response of the measurement system such that random errors are minimized. Right. There are many defects which may present in the instrument measurement system. Say for example, there are connections, there are some say electric circuits which are having some temperature sensitivity. During usage time, it will start building up the temperature of the, say, resistors, capacitors, or some other elements, and because of which slowly it is going to have more and more output shown for the similar input given or the same input given. Say, for example, there can be deflection in the scales. Say, very simple example, there is steel rule, and that steel rule is having some bend in between. So these kind of defects may be physical or maybe functional defects into the system present, that we need to find out by means of again applying the standard input and taking more and more number of readings for identification whether there are the random errors which are present or not. So the system defects are the major reason for the random errors. Like that, there is a unrestrained and parameters that are varying randomly also going to affect on the random error. So the parameters that are varying randomly, say for example, if the instruments are having some parts which are moving or sliding with respect to each other, and in that condition we find there is some dust or some particles are present in between. So probably for first 10 millimeter of the sliding, it will probably not have any resistance, but at particular point there might be some larger, say, element present in between. It will have more friction in between. So further motion, the input may not be reflected because of the friction in between. So it is a randomly varying parameter. Again, if that zone is passed, it may be clear to the next zone. So this is a random variation because of some issues into the instrument. So the parameters may vary randomly. Though input may be constant, output may not be reflected. It is nothing but unrestrained and randomly varying parameters which are going to play a role. So the simple technique that can only be used for taking care of this random error is averaging. That's what I have explained to you in earlier lectures also in discussion, that we take more number of readings and possibly then we may average out. So that will be better nullifying the effect of the random errors, because we have seen that the nature of this kind of random error is nothing but going to have a cumulative effect. Sorry, it is going to have a compensating effect, not cumulative. Cumulative but compensating. The sign may change because of the different sources, the error present may change sign. So the better prediction of this can be done by averaging. A simple way. I think that will again come to know. And in the miscellaneous error, there can be some methods, there can be some say procedural mistakes that can be committed by a particular person. If the same instrument is given, same condition is given for measurement, and two different persons are going to take measurement, it may have some specific way of measuring that is a very person specific, and that we call as a personal or human error, which is majorly responsible for miscellaneous error. Sometimes the interpretation may be wrong. The person or the operator who is going to take the output from the measurement system, he may have some fault in interpretation of the particular element. Right? So it may be because of the faulty component, or because of wrong usage, because of the wrong adjustment that has been made. So sometimes the operator itself take a decision, say in the job shop or some other places, he measure the distance and then he takes a thumb rule that if it is coinciding with this particular marking, then it is to be taken as correct. But that adjustment that he has carried out might be wrong, with some different, say, wrong assumptions and so on. So these are the errors we cannot identify. Possibly the skilled person, if it is asked to measure the same entity under the same condition, probably it will give better result. So again, there is no, say, standard technique for eliminating the miscellaneous error. Say for example, the instrument may be wrongly used. That happens specifically in the depth gauge. You have seen vernier caliper has got a long bar coming out of it, and if that is used specifically for measurement of the depth, you may get very miscellaneous result. Say that can be in the can be quantified as miscellaneous error. Because of different reasons, you will not be able to have the proper sight whether it has touched or not. If it is touching and say there is a gap of say 0.5 millimeter, you will not be able to sense that, you will not be able to see that. Some people or some operator may be very interested to see whether it has restricted by some hard material. He will try to load it again. He will try to give an additional pressure so that the probe has touched the bottom layer or not. But it may not occur if the depth is not sufficient. So then he will take a judgment. That judgment may be based on again the wrong criteria. So what we can say that for the depth measurement, the particular instrument can not give the proper answers. There can be different ways of guessing the depth. Same is the case of angle measurement. Say there is some workpiece or some job on which the angle is to be measured. Say for example temperature measurement, again we as a mechanical entity, or pressure measurement. The instrument might be selected improper instrument. So for the measurement of say 1 bar pressure, if you are using instrument having very large scale, suppose 100 bar is the scale range or 200 bar is the scale range, and that you are using for measurement of 0.5 bar. So possibly instrument is not designed to take care of that 0.5 bar pressure. Then probably you will have to select some different say pressure measurement device which is having a very clear measurement that is corresponding to the smallest unit sensible by that instrument. So in that condition, the only comment we can pass on is the instrument is not properly selected for the given application. Improper application or improper instrument being selected for the entity measurement, both way. Improper application of the instrument or improper instrument for some other measurement. So these are the different causes for the errors. Now let us understand what is instrument error first. So instrument error is basically the inherent sensitivity or inherent characteristics of the instrument which is related to design, construction, I will add further configuration. Now if we go to the measurement system, it will be stages of measurement. Say now suppose I want to have a digital readout for the displacement given for given force. So with this condition I can design or I can have the configuration and stages planned into the measurement system. So if I am going to make the stages wrong, unnecessary stages are taken or unnecessary instruments or primary sensing element or variable correlation elements are improperly selected, then we call that as a poor design. Right. So it may be because of poor design, it may be because of say improper construction, unreliable or unrealistic configuration of the instrument or the measurement system, improper selection of the stages, improper design of the stages, then selection of improper functional elements into, say for example the amplifier, the manipulation element, if it is not able to respond properly to the signal conversion, then in that condition it is going to have the error. Though it is called an instrument error, it can be the measurement system error because of these issues: design, construction, configuration, stages, and so on, multiple issues. Right. So say very simple way it can be say understood by having graduations of the scale. Say if there is steel rule and the steel rule is say it is 1 centimeter, the distance between 0 and 1 centimeter. If I have got this as half, say 0.5, and then improper gradation, say this, I call this 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter. You can see it is not proper. This can be a very simple example. It is improper calibration, improper graduation. So probably if we divide this, it could have been divided properly. It could have came somewhere here. Now this happens mostly when we go for multiple stages. This is very simple example of length measurement. But in measurement systems, say for example temperature measurement, pressure measurement, volume, mass flow, and say other measurements, we are going to rely on conversion of signals from one form to the other. So in that condition, we must take care of the the proportionality. If the proportionality between conversion from one phase to other, the next to the next functional block and so on, in the end it is going to have a simple proportionality constant. So that proportionality must be valid for all the standard inputs that we apply to the measurement system. So that is the meaning of the graduation of the scale. Proportionality should be constant, should be very properly applied to the given input. Now, many times in physical instrument, there can be a balancing of the arm. You have seen that in the grocery shop or in the, say, vegetable market, you have seen that there is measurement device, a null balance device that we call as a lever balance. Now, if I very cleverly shift the pivot somewhere here, then you find that the lever ratio is changed because of this smaller movement by even 0.5 centimeters or 0.5 or 1 millimeter. So because of this, then there will not be proper relation. This will be now L1, which is smaller than L2. So definitely mass 1 and mass 2 proportion will not be constant. Then there will be a continuous error into this measurement. That is what is done or played by the shop owners many times. So if you measure that with accurate measuring device, you will find there is difference of around 300 grams or 200 grams. That is lesser on, say, the entity point of view. We take it, he gives it showing it's 1 kg, but actually it is in practice it is 800 grams or 750 grams. It's because of the balancing of the arm. That is what is the purposeful, say, defect created into the instrument. That is from that trade point of view. But we must be in a position to identify, because we are going to use that as in very technical format. We want to have more and more accuracy of the measurement system. So balancing of the arm is another physical device example, instrument example, where instrument error can be introduced into the measurement system. Then irregular spring tensions, say for example, the spring balance. You might have seen the spring balance. It is having spring inside and somewhere it is connected to some pointer. And then there is a scale on the instrument. And then when we attach some weight here, say load W attached here, the spring may not show the equal deflection. Say per unit change in the weight, say W1, it may have some uneven movement of the pointer on the scale. It's maybe because of the spring tensions. You can say that can be the error. Yeah, maybe unintentionally present because of changing the property, because of changing the dimensions of the spring and so on. You find that it is going to have irregular or say unpredictable spring tensions, because of which there can be errors in the instruments. There are numerous examples of the instrument error into the physical devices. But now we are concerned with mechanical entity measurement, where we are going to have different functional blocks. So it is more or less connected with the stages of the measurement. Maybe in the amplification unit, maybe in the, say, display unit, or say instrument, say signal magnification, signal conversion. There can be some losses or some other additional elements entering into. So then that becomes an instrument error. So it's a very complex situation now. Though we are talking this in very simple way, but for measurement system, it is very important to identify what are the errors because of the inherent elements, physical and functional elements in between the instrument. And we need to remove those. We need to try to remove or make it more closer to zero, right? So this error can be avoided by having suitable equipment for proper applications. See, I gave an example earlier. Let us come to the very first graduation of the scale. You cannot use the scales for measuring value which is smaller than 0.5 millimeter. It's very difficult. Then it is based on the guess. Then we see that if it is magnified, say it is 1 millimeter, standard graduation may be of 0.5. If it falls somewhere earlier to this, then we can see that it is not near to half of this, something later, say I can guess that it is 0.3 something, 0.3 millimeter, because standard graduation shows it is say 0.5 millimeter and this 1 millimeter from 0. If it is in between, then we have guessed. If somewhere it lies here, we can guess that somebody may guess it is 0.35 or 0.45 and so on. So it is, what is the reason? You have selected the scale for measurement of entity less than 0.5 millimeter. That is the mistake. So that is what is the meaning. We can choose the suitable equipment for proper application. Let's take example of the same thing. Say pressure measurement device. There is a dial and the scale on this pressure measurement. If this pressure measurement is having the graduations on, and the range of this is supposed 200 bar, and if one is interested to have the measurement of pressure of 0.25 bars, so probably it is not on the scale itself. So what is the reason? We can say broadly it is a improper instrument or improper measurement system for the particular application. The second way of knowing the instrument error is we try to repeatedly apply the standard input. Right? We try to apply the standard input multiple times, the same input, and we try to find what is the measurement shown by the instrument or the measurement system. So in this condition, we can find out that by means of calibration. So we calibrate that very frequently, and then after calibration, we find that for the given input is going to show the proportional output. Then we apply the corrections and we compensate. We try to compensate. This is very simple for the simple physical devices, but if there are multiple systems wherein different functional and the physical blocks are present in the instrument, it becomes very difficult to know. And that is the major reason where we have difficulty in conducting the experimentations, conducting the different measurements through the system. Right? You might have seen in the practical say demo of your measurement instrument or measurement system, we find there is a fluctuation. Say for example, measurement of the speed. The display panel of the instrument is going to have some kind of fluctuation. Right. So this kind of thing are very difficult to know, but the constant calibration, selecting proper range of the instrument, proper equipment for proper application, correction and compensation, these are the methods wherein we can try to at least quantify and compensate the instrument errors. Any difficulty in understanding the instrument error? Right. Then we come to the environmental and loading error. So out of that, loading error, I think we have discussed. So environmental errors are the one that are going to be entering into the measurement system because of the different elements, entities of subjected to temperature, pressure, humidity, wind forces, magnetic or electric field. Further, it can be say change in the gravity constant, change in the gravity. Then there can be change of the different environmental facts. Say there are some unintentional vibrations into, if your measurement or tool room, say for example into the factories, is nearby some kind of forging device, forging shop, or there's some machining shop, then unnecessary vibrations that are going to enter into, and then it is going to have some kind of vibration of the table, the work table on which measurement is being carried out. So there are different ways in which the error can enter into, which are because of the environment, because of the ambience in which the measurement is being taken. So these are the factors and we try to control them as far as possible. Whereas the loading is the one that is concerned with application of unnecessary forces, unnecessary pressure, unnecessary displacement, stresses to the physical part of that instrument, maybe acting as a primary sensing element or some other say functional block. So the equipment loads the system. Say if I want to have the measurement, now a simple example of say measurement of the distance here. If I am going to have a very touching faces of the jaw of vernier caliper, it is going to show some different thing. If I am going to apply some more pressure, I am going to make it more closer. Probably if the material is say compressible, it's like sponge or some other element which can be compressed, it is going to alter the input itself. And that's what you find, that measurement of the density of such kind of elements which are not having a very solid geometry, it becomes very difficult. That is a simple reason. It's because of the loading. It is the input pressure that is applied on the jaws. It is going to compress the component. And if it is rubber or some other element which can be compressed, it will never be able to have the appropriate reading of the true input. So that is loading. Now this is the other way. The loading that we have studied or discussed in some other places is it will take some input from the system itself of which measurement is carried out. Now in this case it is going to add additional value. Say in this case of measurement, say length measurement, if there is a say eraser with me and I want to measure the particular dimension of the eraser by means of the vernier caliper, then what I am going to do, because of the loading, it may never give the true value of the dimensions. It is the opposing effect. It is not only taking something from in the system, but it is going to alter the system property. Right. So the equipment loads the system and value to be measured is altered. I have given example of the measurement of the dimension of the sponge. In our entity, it is a temperature measurement using the thermometer, having a very large bulb size compared to the system itself. So abstraction in the flow meter, say for example the flow meter or the orifice meter is there, the tube and in which there is a small orifice. So because of this one, there is alteration in the properties. The pressure of the system which is present here and at the other end, though it is used for eliminating fluctuation in the pressure that is going to enter into the pressure measurement device, but it can create the obstruction in the flow meter in the orifice, because that will become more sensitive to even a small obstruction. It will alter the flow. Similar example is a thermometer that is used for measurement of the temperature of the fluid. It is going to alter the thermal capacity of the system itself. So there are different examples of loading. I think that will come across when we go to the instruments, studying the measurement system for given entities. So these are the environment and the loading errors. Any difficulty in understanding this? I think we'll take one or two slides and then we'll stop for today. Then these errors can be either eliminated, or it can be corrected, or it can be made known. Random errors. I think this is the last slide that we are going to see today. So random errors is nothing but inconsistencies associated with the accurate measurement of small quantities. So while measuring small quantities, random error do not give consistent readings. It's very obvious. Say, for example, again the pressure measurement device, the pressure gauge, in which we are going to measure the pressure of 0.5 bar. And the graduation, it's very difficult. The very first graduation, suppose is of 0.5. Then always I have a doubt whether it is 0.5 or less than that or greater than that. What I should call this as? So my first graduation 0.5, it is 1 bar and so on. It is going on. Now small quantity, if it is measured all the time, which is limited to 0.5 bar or less than 0.5 bar little, then the operator may have a guess. He will have to only rely on the guess. Yes, it is equivalent to 0.5 and then it will be something larger than that. He has to assume that as only 0.5. If it is even something smaller than 0.5, he has to assume that it is equivalent to 0.5. So he will not be able to take the proper decision if the value of the pressure is little varying than 0.5 up or below. So this is how the measurement of small quantity always pose a problem. And then that will be always called the random error. So error become noticeable while measuring quantities are of equivalent magnitude. So we can say that it is equivalent to 0.5 bar. Something it may be sometime less than this. It may be 0.45 bar or it can be 0.55 bar or 0.6 bar. Because your instrument is not capable of sensing anything below or beyond 0.5, you have to take guess. Right? So this kind of thing can be taken care by designing the system, if we are going to design the pressure system here, the pressure measurement system, we can make the scale to take care of this. It is possible. So there can be system defects present. Say, for example, into this device, if you have gone through a textbook, I don't know how many of you have gone through even the 12 or 14 figures that have been given, which we are going to ask tomorrow into the test. I think I have made it clear that tomorrow at 12 o'clock we are going to have test number 1. It is for 15 minutes. I am going to give some instruction on the group for the particular test being conducted. It will be MCQ type. All student is going to get different questions, and it will be of very short time, of 15 minutes time. So in this kind of instruments, say if you have gone through the textbook and found out, we can design the scale, we can design the magnification factor, or signal being converted can be made well in tune with the entities under measurement. So the defects can be removed. So there can be large tolerance on the dimension. There can be friction present in the mating parts here. If we go to the configuration of this pressure gauge, there can be clearances, the backlash between the gear and the rack that is used inside the particular instrument. Say, for example, here it is gear profile and it is the pinion, the gear sector. So if there is some backlash or clearance, it may not represent that faithfully to be represented here in the deflection of the pointer. So that can be controlled, that can be minimized. So clearance can be reduced to the minimum desired value. Backlash can be eliminated, or slack in the meter reading or the bearings and the other places, it can be reduced down. Similarly, into the electrical signals, or say conversion through the electrical mode, we can take care of the different issues to prevent the different defects, to give the reading at the output. Measuring the quantity first while increasing and then decreasing the magnitude is going to help to know the behavior of the system. I think in one of the experiment number 1, measurement of the force, I have asked you to go to the hysteresis curve. If you recall, in the practical, we have discussed something like this: upscale reading, downscale reading, and so on. So this is one of the method of knowing whether there are random errors present. If there is random error, you find that it is not going to be straight line. It will have something different behavior for upscale reading, different behavior for downscale reading. So it is the way of having the quantity first being measured while appending the input value and while descending the input value. So effect of the undesired and randomly varying parameters are there. Say, for example, there is voltage fluctuation. There can be current change. If the instrument is working on electrical signals, there can be change in the current, there can be change in the voltage. There can be vibration of the instrument support. The table itself must be shaking. There are some unrestrained and randomly varying parameters affecting the measurement process. Right. So I think I will stop here for today. And again, in the coming classes, we'll start from this. Any doubt till this point, let me know. So I'll ask all of you to go through the textbooks and please join the meeting in the specific time. Today I have not allowed many students to enter into the class. It's only to make you very particular about joining the classes in time. Right. So instruction I am going to pass on for tomorrow's test. Link will be given, and then at that particular time the link will be closed. So you need to follow the instruction very properly. And in the next week, I think we will have 2 more tests, test number 2 and test number 3. So thank you for joining.